So it's a big pleasure to start this conference. Well, I hope that everybody will find something interesting and useful during the meeting. Before start, I just wanted to say that I put the slides on my webpage, so you can download them right now if you want. So maybe it could be useful for following the talk. So the goal of the talk is to present some structures which can be associated from the algebraic geometry point of view to algebraic varieties over finite fields. So maybe these kind of structures could be useful in, well, in other situations. So our objects of interest will be f will be fixed fine field, and x a projective variety, which I will normally assume smooth, of dimension d. So you can think about this just as about an object defined by homogeneous polynomials with some coefficients in your finite field. So in particular, well, lots of people are interested in elliptic curves. Well, we will be mostly interested in varieties of higher dimension for this talk, in particular in abelian varieties. In cubic hypersurfaces, in this case, these are varieties which are just defined by one homogeneous equation of degree 3. We will see that the situation is rather different for these types of varieties. Okay. So now if you want to study them, we may wonder what kind of objects you can associate to X. So this could be a way to start. So let's look for the first option. You can look at varieties of smaller dimension, right? You have a big variety, let's look for smaller ones inside. So you look at all y which are irreducible and of the dimension which, well, some fixed dimension, okay? Smaller varieties inside X. By definition, a cycle is a formal linear combination, just with some integral coefficients, of such subvarieties, okay? And then we introduce the group of all cycles of codimension I or of dimension d minus I, is the same thing here, as this direct sum of this kind of y's with some integral coefficients. Let's see what can it be. So it's too huge, of course, because you can imagine lots of subvarieties are inside, right? So let's see how to make it smaller to be reasonable to study. So you may try to introduce some equivalence relations on cycles. So the very first example is for a curve. So for a curve, you know that you can consider divisors. And we say that a cycle is rationally equivalent to 0 if this equals actually to a divisor of some function. So it's reasonable to consider such an equivalence relation. And so in general, if you consider the cycles of codimension bigger, we also define the rational equivalence in a similar way. So we say that this formal sum is rationally equivalent to 0 if actually, well, it's generated by these notions. So you can also have sum of divisors, of course. And so we consider divisors of functions on subvarieties of dimension 1 more. And so these ones are supposed to be rationally trivial. Okay, so what can we do with this? So recall I just put what we have just defined, the rational equivalence. And so now we introduce Chow groups as factor groups by these equivalence relations. So these are, well, we used to study these kind of groups. So let's see what we get in examples. So for I equals to 0, so I should ask you what we get, because we actually assumed that x was irreducible, and so we get nothing but the class of x. Okay, so we denote, by the way, we denote by this brackets, just the class of the subvariety. Okay. So then, for I equals to 1, well, we just factor by divisors of functions, and so we get the Picard group of x for the curve or for high dimensional varieties. For I equals to dimension of x, it will be just a notation to write ch0 of x as the group of 0 cycles, or the cycles of codimension d, which is the same thing. Well, the point is that still these groups are difficult to determine in general. Even so, they are defined in a more geometric, say, way, but they are difficult to understand. So let's see what else we can associate to x, and this will be actually easy to compute. These are cohomology groups. So let's see what is this. We will be interested in the following types of cohomology because we are over a finite field. So I will denote by x bar the base change of x to an algebraic, some fixed algebraic closure f bar of f. And so one can define the groups of étale cohomology. So with various types of coefficients. So you can think about Z mod L with some twisted roots of unity. So these are nth roots of unity, power to the j, over x bar. And also you may consider the infinite coefficients, which are just defined. It's just by definition as the limit of these groups. And with QL coefficients as the previous one, tensor with QL. And because we are over a field of positive characteristic, we will always assume that this n, L are prime to the characteristic of f. Otherwise, it's just too difficult. Well, let's see what can be said about these groups. So what kind of objects we have here? So let's see what is the size of these objects. Well, they are finite for a smooth projective variety over a finite field. So these ones are ZL modulus of finite type. The same things happens for x bar. And also, this is kind of very classical, and this one is difficult. So these groups, they have no torsion for almost all L. So this was proved by Gaber, and this is a serious theorem. Well, now I was speaking about these groups for x and for x bar. You can relate these two kinds of groups. So by just this exact sequence coming from the Hochschild-Serre-spectral sequence, so you have this object, that one, and also some Galois cohomology group. And so, well, that's it for the moment for the comparison for x and x bar. And to relate these cohomology groups with the previous objects, with the Chow groups, note that we have a cycle class map which goes to this étale cohomology group in degree 2i. There are different cycle class maps which will be also of our interest, and we will consider them a little bit later. Okay, so let's see how can we compute the cohomology. So we'll see that actually it could be very easy. So computing. In degree 2d, d is the dimension of x. Okay, in the degree 2d, you have nothing but just rank 1, C mod n, with this twist. And also in degree bigger than 2n, you have 0. And then you have a kind of duality for degree I and degree 2d minus 1 for the complementary degree. Okay. Okay. So let's see the examples. For projective space, we understand everything quite well. You have one copy of this thing for even degrees and 0 otherwise. So it looks quite concrete, at least. And for hypersurface, you also have a similar formulas, meaning that really like this. But there is one exception. For I equals to the dimension of x, so you see that for 2 dimension, we understand, but precisely in the middle. You have some strange things which happen. So you have the same thing as for Pn, so is a 0 of rank 1, and something more, where this something more is very huge. So you see the rank is really big. So degree of x, it's a hypersurface, so it has a degree as a degree of homogeneous polynomial, which defines x. And so this one, so even for cubics, you see it's already 2 power d plus 2. Well, it's big. Okay. Okay. So what we can say more? So this is maybe this could be maybe of some interest for you. So a recent theorem by David Mador and Fabrice Orgogozo tells you that actually you can compute. There exists an algorithm which allows you to compute these Tate cohomology groups so that you can think that they are computable in the sense of Church-Turing. So this doesn't mean that you can actually compute because it's not effective, or it takes too much time. But still, well, maybe in the future, you can do this, okay? But at least this is something very concrete. Okay.
Is it possible to compute
the Frobenius action? Try to compute in this. Well, we know something. I don't think that they were considering the Frobenius action in their theorem. They were just interested by this. But okay. Well, let's go back to the comparison between the Chow groups and the Tate cohomology. So recall that we have already defined this cycle class map, and then we can consider different ones. So we can consider the one which is after tensorization with QL. Okay. And then you can also go to geometric version. So consider J is a Galois group of F bar, which is just Z hat. So it's very easy. It has, as just said, the one generator. It's a Frobenius. And then C bar will stay for this composition to X bar, fixed by the Galois action. Okay, because we started with cycles on X. And also we have another geometric version, is when you start with X bar already, not with X. And then you still go to the Tate cohomology group of X bar, but because you started over with X bar here, then any cycle will be defined on some finite extension of your base field, which actually ensures that the image here will be fixed by some H, where H is an open subgroup of J. And so we actually have this cycle map. So we have three of them. We will be back for these integral things. This one with X bar here and with bar everywhere. Okay. Let's see what we can say. Okay, so I think that you realized already that you can relate in this way Chow groups and the Tate cohomology groups, which are probably easier to understand. Okay. So Tate's conjecture, the famous conjecture of John Tate, is that the cycle class map is surjective for any L and any I. Okay. Well, it is still widely open, even in the case of divisors. So for the Hodge conjecture, you know that it's known for divisors, but not for the Tate conjecture in this way. Well, I was speaking about other kinds of cycle class map. So, okay, so here are some remarks. Well, in the integral versions, we are interested if we have the surjectivity with the L coefficients. And I wrote here understand, because actually there are some counterexamples. So it's not always surjective, but we will see what kind of counterexamples one can get. And then if you want to think about Frobenius action or about some other cycle class maps, so over QL coefficients, there is actually no difference between considering various types of these cycle class maps, because one can show that this map is an isomorphism, so from X to X bar over J, when you transfer with QL. So what you actually show is that, well, if you remember, or if you go to my webpage and you download the slides, then you can recover the Hochschild-Serre spectral sequence, which tells you that actually the difference between these two is just in this group. But then you transfer everything with QL. And then you have to prove that this one is actually finite, and it is. But it's not at all trivial, so it uses failed conjectures proved by the link. So that, anyway, we can identify these two. Well, let's see what can we conjecture more. So because we cannot prove the conjecture of Tate, so let's conjecture something else. So about the size of these Chow groups. So it is, well, I'm not sure that everybody believes in this conjecture, but at least it exists, that they should be of finite type. But maybe one should believe actually, well, no. Because, well, you may wonder, we are speaking about the surjectivity of the cycle class map, right? What about the injectivity? Why we are not interested in this? Indeed, we are. And so Zi was just the group of cycles without factoring by rational equivalence. And we consider the kernel of this. And the conjecture, so the conjecture would be that the kernel consists of the classes which are so-called numerically equivalent to 0. And this means that, well, actually you know how to intersect cycles. And so so numerically equivalent to 0 requires that any cycle of complementary dimension intersect your cycle, well, the intersection equals to 0. And then one also conjectures that if you consider QL coefficients, then the rational and numerical equivalence coincide. So this is called, I guess, balancing conjecture. So that, all in all, we also believe that these maps are injective with QL coefficients. Okay, so I just wanted to separate several conjectures, but all in all, well, we believe that it is injective with QL coefficients. So maybe you like zeta functions, no? Hopefully. So that's why I put it here. So recall that for finite field, we can define this function. You count the number of points of x over all extensions, then you consider this power series, and then you put zeta function of x as this one. And then from the well conjectures, it follows that the poles of zeta are on these lines. Okay, now you can be interested in the order of the pole, and then in the strong form means that it actually implies the previous one I gave you. So we conjecture that the order at I of the function is exactly minus dimension over q, well, I wrote over q, of the factor by this numerical equivalence. Okay, so whatever context you prefer, you can find some conjectures to think about. And so let me consider some cases where we know or we do not know, like let me be more precise about these versions of this conjecture. So the case of divisors, so codimension 1. Well, for divisors, it's actually quite easy to see that one has this exact sequence. So this is precisely the cycle map we are interested in with even the L coefficients. And then we understand the cokernel in this way. So it is the cokernel which we are interested in, okay, in the Tate conjecture. So we understand it. So what can be said? So this last group has no torsion just because of its harm from this one. Okay. It has no torsion, and it follows that the surjectivity with integral coefficients is actually equivalent to the surjectivity with QL coefficients. And it's also equivalent to the fact that the brow group of X, well, I do not say what is this, nobody objects, so everybody knows. So, okay, so for the finiteness of this group. Okay. But still it's open, even if it's equivalence, it's two versions, but they are in general open. Well, in the case of 0 cycles, it's a result by Colliot-Helen and Sansuken-Soulet, which tells you that actually there is an isomorphism. So everything works well for 0 cycles, hopefully. Well, 0 cycles in this context are supposed to be easy. Well, what more? Well, speaking about the torsion, so the torsion, it will be about the kernel of the cycle class map for codimension 2 cycles. So there is a result saying that you have injectivity on the torsion. But actually, I found no information about the higher codimension here. So could one have, for instance, that the kernel here is non-zero for some L and for RA3, I don't know. So it's, well, it's open. So you can start thinking about this, but actually it's open. Okay, so let me present some known cases of the Tate conjecture. So for divisors, indeed, in some cases we know the conjecture is for divisors on abelian varieties. And the precise version here is this one. So if you have two abelian varieties, A and B, so this tensored with ZL is actually, so this map, well, I didn't write it. It's an isomorphism with the hum over QL of these Tate modules, where Tate module is defined in this way. And I wanted just to observe that over C, so, I mean, more or less everything in the cohomology is generated by H1, but over a finite field, there are some classes which are so-called, somehow exotic, and they are not coming from this H1. But anyway, we have the Tate conjecture for divisors and abelian varieties. So this was established by Tate himself in the case of finite fields. So recently, also Tate conjecture for divisors was proved for case-free surfaces. And for case-free surface, as examples of case-free surfaces, you can consider quartic and P3, or double cover ramified over a surface of degree 6. So these are concrete examples of case-free surfaces. And in a characteristic different from 2, by François Charles, David Schmaulik, Kirsty Medapusipera. So we know by their work, we know the Tate conjecture here. And also for some other, I wrote specific varieties. So this specific more or less means that they have lots of symmetries, which actually allows you to construct lots of cycles. So that is more or less all for divisors. And also things could be nice for products. So in particular, if the variety X is dominated by some product of abelian varieties and curves, so then it's okay. So we know Tate conjecture for divisors, because actually it holds for I equals to 1 on the product, if and only if it holds for X and for Y. So let's see, example. You have this variety, so you have 4 variables, okay? So we have this one, it's a surface. It is dominated by the product of 2 curves. These are 2 curves. So that's it. We know the Tate conjecture for this one. So, and so also maybe I put one remark to say why actually this Tate conjecture holds on X cross Y if and only if on X and not Y. Because at least for curves we have this nice formula. These are Jacobians, and this pegs X and pick Y. I forgot the parentheses here. And you have a similar formula in higher dimensions. So this helps you to prove this. And I also found it a good place here to put the second remark, even if it is not directly related with this, but maybe it could be of some interest for you. So actually, if you consider the 2 elliptic curves, so because we're speaking about these harms, etc., so if you consider 2 elliptic curves, then it's a recent result which tells you that if you consider them over a number field, and then you consider the reductions of these elliptic curves, then there are actually infinitely many places where the reductions are geometrically isogenous. This is due to François Charles. And what can you say more? In particular, if you pick one elliptic curve over this number field, and then you look at reductions of E, then at infinitely many places, either E has a supersingular reduction or has complex multiplication at infinitely many places. So it's somehow related to this discussions with homomorphism, etc. Okay, so that's all about products. And so now let me speak a little bit about integral versions. Okay, so in integral versions, the goal is to understand the surjectivity of the integral cycle class maps with ZL coefficients. Okay, so this one, or when we go to X bar, G stays for the Galois group still, and this one. And it turns out they are all different. So it could be, there exist some examples of surjectivity in one place and not in another one, and none of these need be surjective, okay? So there are counterexamples everywhere, so we will consider these counterexamples now. So what could be the obstructions for the surjectivity here? So we understood that for I equals to 1, we have what? For I equals to 1 here, what should we have? It could be counterexamples here for I equals to 1. Do you believe? Who believes to counterexamples for I equals to 1? No, but it's okay, because I just, well, in the previous, somewhere here, okay, let me go back. Okay, so it was here. We saw that these are actually equivalent, okay, surjectivity for with L coefficients and QL. So if you believe in Tate conjecture with QL coefficient, that you shouldn't get any examples for I equals to 1. So we have to consider I at least 2. And I will present two types of abstractions. One of topological nature and another one from algebraic nature. So the first one is a classical one. Well, it comes from the classical argument of Algebraic. Oh, well, sorry, there is a mistake here. So then revisited by Tatara, by myself and Yagita, Kameko, and recently by Antu. So what is the subject here? So these abstractions give you examples where this map is not surjective. Okay? And even if you consider the group, but you mod out by torsion, so you can also have a counterexample. So you have, from the structural point of view, here you can have all kind of counterexamples you may have. Okay? So everything that you want, you can have here. So these topological abstractions are based on the existence of some kind of cohomological operations, so it is still about cohomology, on this Tate cohomology group, but I was not precise about which kind of groups we consider because they are somehow of motivic nature. Some of these operations, so the precise one which will be of interest for us is Q1, so-called Q1. So this should vanish on classes of algebraic cycles. So this is all this construction, well, in the algebraic setting, it is due to Voevodsky. We understood that if we produce some cohomology classes such that Q1 does not vanish on these classes, so they couldn't be algebraic. So that's the method. Now, how to produce these classes which are not in the kernel of Q1? Well, actually, from the topological point of view, if we do not consider the Tate cohomology of X, but we understand the cohomology of groups, just abstract cohomology of groups for these very easy groups, just Z mod L to some power. Okay, so, and these operations, they are kind of analog for usual operations on these cohomology groups. So now the question is how to produce an algebraic analog for this. And here the explanation given by Tatara is that actually you can replace your group J, which is finite, by some quotients, which are actually algebraic varieties, where you realize your group J so that it acts freely on some quasi-projective variety U. And if it's U big enough, then you can take X as a quotient like this. Then actually you can relate these computations for the cohomology of the J and of this X, and you can compute for such X. Well, now if you have some intuition or reflex in algebraic geometry, you would say, oh, but what is this? It's actually quasi-projective. It's not of our interest. We are interested in projective examples, and actually you can produce some projective varieties which miss more work. I put here hyperplane sections, but it's not so easy, but still you can do this. And then going back to this question for torsion, okay? So if you want to find some classes which are not killed if you're mod out by torsion, then you should actually consider more complicated J's, not these ones, but like exceptional of type G2, F4, if you're a fan of E8, this is also okay. And this is actually the point about these groups, is that they contain Z mod L inside, and then you can relate these groups and these computations. So I was just intending to give you an idea about which kind of things we use here. So that's it for the topological abstractions. And now let me consider some algebraic abstractions. Well, actually for I equals to 2 again, so for I equals to 1 we understood, I hope that we shouldn't expect counterexamples. So for I equals to 2, we can understand, so which actually means for us just expressed differently. Okay, so well, maybe this different expression could be useful. So we can understand this the torsion in the core kernel of this cycle class map for C2. Okay, and this comes from the work by Bruno Kahn and Colliot-Helene. Well, what we do? If you consider your variety X, then you can consider the field of functions of the variety X. Okay, so it's a field, it's a huge field of the transcendence degree dimension of X over the finite field. Then, for the field, you can consider the Galois cohomology groups, meaning that you, as a group, you consider the Galois group of this f of X, of this big field, and well, with some coefficients, z mod L or mu L tensor G coefficients. Okay. And then, which is useful for us, it is to consider some subgroup inside. Okay. So, what is this subgroup inside? So you consider so-called unramified elements here. So it's well, to define, it's not so complicated. You just say that an element is unramified if it has no residues. Well, there are some formulas, very explicit formulas, to define the residue maps on these cohomology groups. And well, these residue maps, they are attached to some valuations on this field. Well, you have many of them. You have really plenty of them, infinitely many, even. Yeah, and so so you define the unramified cohomology group as a subgroup of this big one, consisting of classes which are unramified. Okay, so why this could be useful? Okay, so because well, you can also consider these groups with these coefficients, or even with infinite coefficients. Again, it's a problem with just by taking a limit. So here is the big. Why is it useful? Why I'm speaking about these kind of things is that the co-kernel of these maps, the torsion inside. So that's what I was intended to do, the torsion, because by the Tate conjecture, well, the problem should be only in the torsion here. And so this is actually this unramified cohomology group in degree 3. And this holds if this last group, meaning this H3 unramified, is finite. And if this group is infinite, we also have a formula, but you have just mod out the divisible part. But actually, conjecturally, this one is always finite, so that's why I put this in this way. So this formula should be correct always. Okay, so this expression could be somehow, sometimes it could be useful, because sometimes you can compute, you can find some non-trivial elements inside. So let's see what can we do. Well, in general, what happens is that this field and its Galois cohomology, it's actually very difficult. It's very huge. It's difficult to understand. But in some cases, it's not so difficult. It is in the following case. When you consider X a quadric, so if you consider a variety which is defined by homogeneous equations of degree 2 over some field big K, it will be typically different from the finite field, but still, what happens is that you understand quite well these maps, which relates the cohomology of K and the cohomology of the function field of the quadric. And this goes back to the work of Arasan. Okay, so, and this can be used, this construction can be used for X here, when X has a map to some smaller dimensional variety with generic fiber a quadric. Yes?
So it can be a function field or is it the transcendent or the base?
Yes, it's well, this one typically it will be of transcendence degree, or big K, you mean? Or yeah, it will be of transcendence degree 2, and you will see actually, because that's the point that you take for K the function field of Y. Okay, so this is the situation. You consider X constructed such that the function field of X is of this type, but for some big field K. Okay, so it's okay. Sorry?
It's a bundle of quadrics.
Yeah, it's a fibration in quadrics. Okay, so let's see. Okay. Well, fibration in quadrics of dimension 3 or 4. So in this case, you consider S a smooth surface, X a fibration in conics. So your big field K, so K is the function field of X. So for transcendence degree 2. And then Parimala and Suresh established that you have no unramified cohomology group here. And this actually allows you to deduce that you have the surjectivity here for the cycle class map with integral coefficients for a geometrically ruled S. Typically, you take S equals to P2. Well, let me write something here. Well, in this example, okay, S equals to P2 over finite field, for example, and big K will be F of 2 transcendental variables. Okay. So indeed, so this is the type of this field. So this is in dimension 3 because the ambient variety axis of dimension 3, and in dimension 4 it's open. So you have another open problem. Probably this one is easier than the previous ones. And then in dimension 5 you can actually produce examples still over P2 with non-trivial non-ramified cohomology groups. And you can compute all these residues. You can do this, it's just a computation. Maybe you can even optimize with some computer programs, but well, I was able to do this just by hand. And for such X, because of this, the fact that it's non-zero, so these are not surjectives. And I just decided to write down the equation of the quadric we consider. So these are variables, x0, x1, x2, x3, x4. And you have some coefficients, A, F, AF, G1, G2, where you can explicitly take A, some non-square element, F, just x over y, where these x and y are here, okay, so for this field. And JIs, they are also quite explicit, but they are huge. So you can consider just fractions of products of 8 linear forms. So you have 8 linear forms up and down, and for some choice, it works. Okay, so at least it's very explicit.
And do you know if the H3 is finite?
Yes. Yes. Okay. Well, now it was a lecture, and now we start with problem session. So let's consider some examples. Well, I put cubic curves just for memory. It's very easy in this context. So meaning that, well, of course, you have to have a point. Well, consider elliptic curves, okay? So here we have the Picot group of E, the points of E and Z. Well, what I put here? Well, anyway, for a peak here, you have here this isomorphism. Anyway, so what I wanted to say, and everything is very easy. And I didn't put the cubics of dimension 2 because this will come later. It will be more difficult. For threefolds, it's actually very easy as well. So what do we have? A threefold is just a cubic threefold is just a hypersurface in the projective space of dimension 4. So I gave you formulas for the cohomology of these ones, right? So trivial of rank 1, well, rank 1 in even degrees, and 0 in odd degrees. Okay, so this is over x bar, these ones, okay? They are ZL just for I between 0 and 3. And by this Hochschild-Serre spectral sequence, because the difference is situated in degree 2i minus 1, but we understood that in degree 2i minus 1 for this cubic there is nothing. So you actually have this isomorphism. So you understand all the cohomology groups, and they are very easy. This is just ZL. Now you want to know whether you can realize the generators of this ZL as classes of algebraic cycles. This was the question. Okay, let's see. Okay, this is clear because it was an example in the very beginning. There is only the class of X here. Okay, for 0 cycles, well, it's actually also trivial because I formulated a theorem that tells you that actually you always have an isomorphism for 0 cycles. But here we know that in addition, this group is just ZL, and any irreducible variety of a finite field has a 0 cycle of degree 1, because you can actually use the Langweil estimates here, and so this gives you that you have always a surjection to the factor of ZL. And also for divisors, you have isomorphism here, because the 1 here is generated just by the class of a hyperplane. And the somehow something which is not trivial, this is more or less, this is true for any, well, these 2, 1, 2, and 3. 3 points work for any variety of a finite field. And now for cubics, there is something special that the cubics, they have lines. Well, of course, here we are not over an algebraic closure, but still, because of the lines contained in a cubic, you will always have an isomorphism here. And this group is still ZL as before. So we can have 1 as a class, and well, maybe we will not find a line over the field itself, but some formal combination of the lines over field extensions will give you this isomorphism. So please ask me questions now or afterwards. Okay, so now, though it was actually not very difficult, and now let's consider cubic surfaces. So a cubic surface in P3. So we have here isomorphism still for 0 cycles. And for PK group, we understand X bar, because we understand this pretty well. It's just a blow-up of P2 in 6 points for a cubic surface. So that we understand also PK group. So I forgot to put here ZL, but never mind. So over X bar, it is ZL power 7. But what can we say about X over ZL, over the base field? Well, it's actually not so clear, because you can have different ones for different cubics. And there are some tables in the book of Marin, but still it's not trivial here. Something more complicated happens. Now for cubic fourfolds. So X in P5. So we still have some trivial cases as for cubic threefolds, for divisors, for curves, because we will still have an argument with lines, and for something in the middle, it is more complicated. So let's see. We have, okay, similarly, for 0, 1, 3, 4, we have an isomorphism here. And the missing part here is I equals to 2. And recall that for I equals to 2, we consider H4, and H4 is precisely the middle cohomology. And recall that I give you formulas for the rank of these groups, and they are actually very big, right? So it could be difficult to understand whether we have surjectivity here, because we have lots of classes to realize. And what here is what we know. The Tate conjecture holds for CH2 of X, but it is not trivial. It's a theorem by François Charles. And an integral version in this form is also true. So this map is surjective, so it's what we need together. But for this integral version, so for a different one, we still don't know if this is surjective. So it's another problem to think. Lots of problems. Okay, so that's everything I wanted to say. Thank you very much.
So thank you for this nice talk. Are there any comments or questions?
Yeah.
You return to topological examples.
Are they explicit in the case of exceptional groups?
Well, when in the case of exceptional groups,
yes, yes.
You take this, well, yes and no. Okay, so you can
For example,
consider
at least the dimensions.
Yes, the dimension is a smaller one. The smallest possible can be realizable. Yeah.
It means what? As small as possible.
So here, so it is for CH2. So you want CH2 equals to dimension 2. So it's dimension 4.
Ah,
okay.
So.
Because actually, what happens is that you still realize first you start with these quotients. You consider U quite big, but this U is very explicit. You just take some matrices of rank on fixed rank, and then it's okay. And then you have to take hyperplane sections and to use some kind of base change argument from C to a finite field, not from C, but for number
these
field.
plane sections are just some generic sections.
Some generic, so that you have some smoothness, and then yeah.
Okay. And also, just a silly question about cubics in dimensions 3 and 4.
Yeah.
Are they non-rational? Some of them here.
Well, it's over finite field. Okay, so.
Yes, I understand that over C it is well known, but here.
Good question. So,
not sure.
So of course they are not rational over C. These ones. In dimension 4, you know that over C there are some which are rational. In dimension 4, but in dimension 3 they're never rational.
Yes.
And I think that you can, yeah. You can probably produce some of them which are not rational. Maybe we can discuss, but I guess that actually you can produce some which are not rational. Mm-hmm.
Any other question or comments? Perhaps I had one.
Yeah.
I assume you're using smooth algebraic varieties.
Yeah.
Would that theory sort of you could try to apply it to singular varieties, or you would need the resolution of singularities?
Well, the point is that, well, here one usually considers these conjectures over for smooth varieties, and I think that an important point is the purity. So it gives you lots of like flexibility, etc. And probably it could, well, I don't know, maybe it's also easy to produce some counterexamples for at least for integral versions. For instance, for quasi-projective, it's very easy to produce some counterexamples. It's really easy. So could this be used for singular ones? Well, I don't know. So no, I think just it's kind of a habit to use these smooth varieties. So.
Any other questions? Well, if not, then we'll resume at 10:20, and we may thank the speaker again.